Hi everyone, this is lesson 1.8, represent functions as graphs. In this lesson, we're going to graph a function with its domain and range, write a rule for a function using its graph. So for graphically representing functions, given a table of values that represents a function, we can graph the values on a graph using the Cartesian coordinate plane. You are familiar with the coordinate plane. It has your x and y axis, and that's where you put points. So each input and output in the table make up an ordered pair. And you list an ordered pair, using parentheses, like x comma y. Then which are plotted on a graph made up of two intersecting perpendicular lines. These lines are called axes. And they divide the graph into 4 quadrants. The horizontal axis is the x-axis, and the vertical axis is called the y-axis. The way I like to remember the difference between horizontal and vertical is that you give a horizontal hug, like with your arms sideways, and a vertical V. So V is pointing like upwards, but also like downwards. So it's kind of a stretch, but it could be a good way to remember the difference between horizontal and vertical. So we put input values called x coordinates, because input is x, horizontally along the x-axis, and output values called y coordinates. I think that you probably already know this, but it's a good refresher. Vertically along the y-axis. And here are just some examples of ways you can represent functions. So here, this is just your coordinate plane with the 4 quadrants. So you always start with 1 at the top. So this is where both x and y, that's not what I meant to do. Both x and y are positive. So this is a positive x, positive y quadrant. But here, if you go left and up, that's the second quadrant, then that would be negative x and positive y. Negative x, positive y. And then if you go left and down in the third quadrant is both x and y is negative. And then the fourth quadrant is a positive x and a negative y. Positive x and a negative y. So in the first and third quadrant, they both have the same positive or negative sign. So these first quadrant is both positive, third quadrant is both negative. And then in the second and the fourth quadrant, they're either positive or negative. So looking at the table here, you have your input pairs and your output pairs, and you can take a table of input and output pairs and put them into actual ordered pairs. So 1 and 2 make up 1 and 2. 2 and 3 is written as 2, 3. 4 and 5 is written as 4, 5. And then furthermore, we can put these on the graph. So 1, 2, 2, 3, 4, 5. Those are the 3 ordered pairs that were in the table. So let's look at some examples. And in this lesson, you're going to want to have your graph paper out. So hopefully you have your graph notebook with you, because we're going to be graphing functions. And when you first get out your graph paper and you're working on a problem, you're going to want to set up your x and y axis like whatever the problem is. And if it doesn't give you an x and y axis, you could just make a general 4 quadrant 10 by 10 coordinate plane if needed. You might also want to think about like what where is the function in relation to the x or the coordinate plane? Like, do you need all four axes, or maybe you just need the first, or do you need all four quadrants? Maybe you just need the first quadrant or the fourth quadrant, or maybe you just need the first and the second quadrant. So when you're ever setting up your coordinate plane, think about which quadrants you need and how far you need to go. Like, do you need to go all the way up to 10, or maybe you need to go further? We'll do a lot more with that later, but just some food for thought for now. So graph the function, part A, graph the function y equals 1/2 x with the domain 0, 2, 4, 6, and 8. So they're specifically giving us the domain, the x values. So in order to graph the function using these specific domain numbers, we are going to need to find the range numbers. So let's make a table of input-output pairs. And remember that y is equal to 1/2 x. So when I say y, I'm saying we're plugging in these values of x into the function. 0, 2, 4, 6, and 8. So when x is 0, y is still 0. When x is 2, 1/2 times 2 is 1. When x is 4, 1/2 times 4 is 2. And then we're just multiplying each x value by 1/2. Okay, so then let's plot those points. And you'll also need your straight edge. So if you have a ruler, or you can use your student ID card for straight edge, but you never, ever, ever want to draw a line with free-handed without a straight edge. So get your ruler out. So our points are 0, 0, 1, 2, 1, 4, 2, 6, 3, and 8, 4. And I'm going to get, well, actually, in this case, since these are just our specific domain numbers, we're not going to draw a line through them, because that would imply that the points in between them are included, but they're not. It's just these 5 points. So this is all that we're going to do. All right, let's do the next one. So the next function is 2x minus 3 with the domain of 2, 3, 4, and 5. So let's make our x and y input-output table. We're using 2, 3, 4, and 5. If you have a different color, you can use it. And then we're plugging in 2 into the function. So 2 times 2 is 4, minus 3 is 1. 3 times 2 is 6, minus 3 is 3. 2 times 4 is 8, minus 3 is 5. And then 2 times 5 is 10, minus 3 is 7. So let's plot the points. So 2, 1, there's an overlap point. 3, 3, 4, 5, and 5, 7. All right, so that's it for that example. Let's go to the next one. So example 2, a real world example. Okay, so in this example, we're going to also talk about scaling. So a table, let me spell that out for you. Scaling. So scale, kind of like scaling. So setting up a scale for your graph. The table shows the average score S on the mathematics section of the SAT in the United States from 1997 to 2003. Don't feel like you have to write all of this down. Just write the important things down in your notes. As a function of time in the years since 1997. Okay, so whenever it says something like that, it means that 1997 is the year 0. So when it starts at 1997, that means that when t equals 0, that's actually talking about 1997. When t equals 1, that's actually talking about 1998. Okay? In the table, I guess it says that in the problem. Okay, so I first identified the independent and the dependent variables. So independent is your input variable, your x, and then the dependent variable is your y. So which one would be the x variable? So I guess I should show you the table. I wonder if I can move this up a little bit. Nope. Okay. Well, so whenever you're dealing with time or years, that is always going to be the x variable. That's always going to go on the x-axis. So the independent variable in this case is years. And then the dependent variable will be the score that they receive. So when we're setting up our table, when we're graphing the function, the first thing we do is set up our x and y axis by labeling the x and y axis. So let's label the x-axis as years since 1997. It's good to be descriptive. And then the score Okay, so let's look at the table. So we want to graph these points. Now, in order to set up a table, our x and y axis, we want to try to use the whole graph that is given. Now, it's going to be a little different for you since you have graph paper, but consider that you're given the same amount of graph paper as in this problem. So if we were just to start here at 0 and then go 1, 2, 3, 4, 5, 6, we would have all of the space here left over. So in order to actually use this space, we can change the scaling so that it's not every one tick is 1 year, but perhaps every other tick is 1 year. So I'm going to go every 2 ticks represents 1 year. That way we're just spreading out the graph a little bit. Oh, and then it's, wait, no, I skipped the number, didn't I? This is supposed to be a 5. Okay, and then on the y-axis, we go from 511 to 519. All right, so let's talk about how we're going to scale in this case. So should we go like by 50s? So if we went by 50s so that we could get all the way up to 500, notice that we're only working with a range of 8 here, from 511 to 519. So if we did that, then our points would be like just very condensed in the vertical part. So in order to space them out, we can actually make what's called a break. So a break, I think you're familiar with this. If you draw like a little squiggle here, a break means that you're going to skip. We are going to skip from 0 to, we can actually even skip just to 510. So we're going to let the first tick here represent 510, and then just go up by ones. 511, 512, 513, 514, 515, 16, 17, 18, and then 519. So notice I didn't actually write down all of the numbers, but at least write down the first and the last number and a couple in between. You can even go like every other. So maybe you could just do the even numbers. That way your graph isn't so cluttered. 516, 518. Okay, so now that we have our graph set up, looks all nice, we can plot our input-output pairs. So 0, 511, 1, 512, and then back to 511, 514, another 514, we have a 516, and then we have a 519. So it looks like the scores are getting better over time. Suppose part C says suppose that you use a table, they use a scale on the S-axis from 0 to 20 in increments of 1 unit. Describe the appearance of the graph. So this is kind of what we talked about earlier. All of the points would be condensed at the top. All of the points would be condensed at the top. And then you would have a lot of wasted space. All right, let's look at some examples for writing a rule for a graph. So here in part A, one thing we might want to do when we're given a graph like this is just write out the numbers in the table. So I'm going to rewrite the input-output pairs as a table. So this would be 1, 2, 2, 3, 3, 4, 4, 5, and 5, 6. So what pattern do you notice? So what are we doing to x to get to y? Well, this one is actually pretty simple. We're just adding 1. So this one is just y is equal to x plus 1. How about part B? Let's make a table. So we have 0, 5, and then we have 1, 4, 2, 3, 3, 2, and 4, 1. So what is going on here? Well, notice when x is equal to 0, y is equal to 5. So, and then after that, you are subtracting the value of x from 5. So 5 minus 1 is 4, 5 minus 2 is 3, 5 minus 3 is 2, and 5 minus 4 is 1. So this rule would look like 5 minus x. One thing to note, though, is that usually we are going to learn how to write our equations so that the x comes first in the equation. So if you were to flip these around, it would look like y equals negative x plus 5. So the negative sign actually stays with the x, and then the 5 is actually positive. So it would turn into plus 5. And then part C. So let's make our table so we can get a better idea of the numbers. 1, 10, 2, 15, 3, 20, and 4, 25. All right. So this one is kind of tricky. So here we want to ask ourselves, are we adding something? Are we subtracting something? Are we multiplying or dividing? Or maybe a combination of the two of these. So this one's a little tricky, so I'll give you some hints. So you can tell that you're not really adding something to x each time. However, you are moving up in the y by 5 each time. What that is called is the slope. So if you remember, slope is the number that's multiplied by x in the formula y equals mx plus b. So actually our m here, the number that we multiply by x, is going to be 5 because you're moving up by 5 in the y. You're increasing by 5 for each x. So y equals 5x, but that's not all, because 1 times 5 is not 10. 2 times 5 is not 15, it's 10. 3 times 5 is 15, and then 4 times 5 is 20. So actually we have to add an extra 5 in order to make this function. So 1 times 5 plus 5 is 10. 2 times 5 is 20, plus another 5 is 15. Okay, so this rule actually would work. All right, so that is all for this lesson. Next, we're going to work on the edge elastic assignment.